Well, we just did that. So, there you are. So, okay. So, I'm glad I got that right. Very well done, boys. Good. Predicate. Predicate object. So we've got predicate, objects, modifiers, and all that good stuff. So for all, there exists, and we can use the invalid arguments again. So you all remember these. We love them. Effectively, how to read this is for all x, so for every x, there is a y such that the x we pick to start off with belongs to that y. So if we just got this whole set of possible people, you pick one, basically for everyone you pick, you can find someone else that that person knows. So you do need to read them from left to right, because the order doesn't matter. We obviously looked into sets. So we've got lots of set constructions, union intersections, differences. Also, we can use predicates to define set membership. So a set of all natural numbers that are even would be an example of that. Set enumeration, listing all the elements of a set. Set comprehension, and Venn diagrams. So, I just heard that we should get on in this lecture. One more. 25. I just assume that it's just one playground or pressing the wrong button. scenario where number 1 is actually true. That's right. We've got two distinct sets basically. So we've got set A and set B, and basically there's nothing that they share. None of us in the norm. But in the general case, obviously we've got these things being slightly bigger and overlapping. So, well, I think I've redrawn it. Right. That's the same thing. Anyway, moving swiftly on. Obviously, we're counting these elements twice in that intersection, and hence you need to remove at least one set. Well, if you did the coursework, you should know the answer.
1.
Or quite a few people out, and the equivalent question.
I reckon like 1. What is that? 1. First one is the most important part. No, not 1. Yeah, I think 19. What?
Okay, so
What?
of course 19 is obviously right because it's odd and it's greater than 10. So both of the scenarios, in this case, this is true and this is true. So from truth table point of view, that is correct. Now, if I plug in 3, then 3 is odd, so that's true. But obviously 3 is greater than 10, so that would be false. So overall that thing would be false, so 3 is within. But 12 is odd, no, that's false. And hence by implication, truth table, basically the overall thing is true. So when you plug in 12 here, this statement, this predicate becomes true. And hence 12 is in there, for the same reason 8 is in there. Does that make sense? So we then progressed to continuing products and power sets. And that then led us to the lovely relations that you all came to care about with slides of location, associated relations. So domain, range, restriction, domain range, anti-restrictions, all this sort of stuff. Relation images and inverse images, whatever else. So basically, the things that we got out of that was a way of extracting or storing information in relation. And funnily enough, I mean, you're all using MySQL or something for your coursework with Tues. It's a relational database. Guess where they got the name from? So basically, relational database is nothing but a configuration of this type of relations. So, and all this sort of domain restriction stuff is effectively just where clauses in your SQL statements so that you get stuff out of the database. It's a relation table. Relation database, effectively you've got tables, and I've got relations to other tables, or keys. So, this is sort of the mathematical foundation for those relational databases. Anyway, here we go. Come on. Okay, so that's how it works. Let's see whether that works. Yes, okay. Let's see whether they're going to try it now.
So hard. I'm really tired to get it right.
Yeah, I know you may.
I know, I just don't really give a shit.
So what about someone is going to mess it up?
That was 7% seriously answered ABC. like legit thought it was ABC.
Not quite sure what 7% of 27 actually is. That's quite what it is.
Sean. I'm still playing. I'm still playing.
Tried our best. This class just doesn't want to.
Still a little more outside these.
Weird.
Okay. Yes, so this is the domain restriction. So effectively we're looking at the relation and restricting it to the elements A and C. Now C is not involved in the restriction, so
I will tell it.
so A is not in the restriction. So C is not involved in the relation, so we're just looking at A. And so the only ones that are we're going to say 1 and A2 as well. So, and yeah, basically this still, because it's a domain restriction, still gives us relation, so we still need to have ordered pairs in our sets. So this is how we extract information from relation.
Yeah. That's
So in effect, you sort of read this from the inside out. So you start off with the bit that's inside. So we've got a range restriction to CS154. So you're only looking at ordered pairs that involve that source. So it's a select where all equals CS154. And then we're just looking at the first segment of that ordered pair, which is basically people. So yeah, it's people registered for CS154. We then progressed to a special kind of relation, functions, and looked again at partial, total, surjective, and bijective versions thereof. And basically, because functions are just special kind of relations, all the relation notation we used beforehand still works. Which we then use basically to put it all in together and create a system that uses our set notation and relational notation and compositional logic to describe systems. And that's exactly what we do in Java as well, basically. So we've got these parts of the property machine, which basically allows us to specify the sets we're using, any variables, and what this machine needs to satisfy all the time. And then we can specify operations on this. Basically, just like methods of a class in Java, those operations basically operate on the member variables that we got in the Java class, which are basically our variable sets and constants. The advantage we have over Java is that basically we can specify what always needs to hold, which you can't easily do in Java. And that allows us to actually check that our machine keeps those states in check, basically, so that we don't violate the invariants that we created. So they can still read correctly.
I måste smyga det and then
sorry, I won't make it. That's my bad.
One song that I'm actually one DJ.
You're gonna have to play the jump. Don't prove it. That's fair enough.
One website.
Right, very varied. Okay. So we don't really care about, this looks okay. The bits obviously we're interested is this part. So this says class is an element of a power set of students, which basically means that class basically contains a list of students. Here we now say complete is a subset of a power set of students. So that would be effectively say the set of sets of students, which is not quite what we want, I don't think. This one just says that the size of the class needs to be less than 30, or equal to 30, and here's a condition that basically you can't be in the class and have completed it already, and we express it by saying that the intersection of the class and the set of students that have completed the class must be empty. So, effectively, the thing we need to change is this part here, basically, where you said complete is a subset of the power set, because that doesn't give us what we want. We want a set of students again. So we need to have the same definition for completed as we have for class. So we can either change it to what I've said here, or we could just say it's the same principle as class, so class is an element of the power set. Either would do, but I probably has so much space. So, however, to your relief, as you probably saw already, in the actual exam, I won't ask you for pro B syntax, or I won't be asking you questions like that. Although the actual question could have been, how would you express that no one can be in the class and have completed it? That would be a valid question, and then I would have expected you to write something like class intersection completed equals the empty set. And the last part we did basically was all around mathematical functions. So basically being able to draw a graph of a function and use that to determine its range or its domain. Then looked at limits and briefly went into the differentiation of functions as well, which we then used to work on some optimization problems.
Is that for a read file?
So, in terms of revision, you've got obviously all the lecture notes with answers. You've got the weekly tests we went through. Well, not weekly tests, but tests that have time tests. So go over them and make sure that you can do them.
How long was it reported?
And then basically go through the exercises on limits and optimization on the website. And that's pretty much it. We've got some time left, so if you've got any things that you want me to go through in particular. Maths.
Not many though, just mostly.
Okay, anything in particular? Explain maths.
There was one optimization problem in one of the tests when I was dropping. It was the one that I asked you about before. It has to do with like the widgets or something.
Widgets?
Yeah. No, not widgets.
Oh, is it the factory currently employs 10 workers who in terms of going through the whole of maths, that's not going to happen. I need a bit more detail.
Why would you want to do that?
When you have like bed bugs,
That means you just like end up taking a nap with when your friends are over.
no, I don't know, I was just like, Hannah, we wait like, some night, I'm tired, and we go for a walk, we go walk around oh, it's so barely stand up. Smash that, it's so cheap as well.
Thank you. Thanks once again. Once again, thank you.
Right, so we've got the factory currently employs 10 workers to assemble 60 widgets per hour. For each additional worker you employ, the assembly rate goes down by 2 due to people having to wait longer for parts. Okay? So, how many workers can you still employ before it becomes counterproductive? Are you actually reducing the output by hiring more people?
Yeah, take it.
So what we've got is, we've got 10 people at the moment who can output 60
Yeah, hello.
widgets. Okay? So,
Hello.
if we add one person, 11, then instead of outputting 60, they only output 58. So,
Wouldn't that just be a linear function then?
right? Well, if we hire 12, we get 56.
Yeah, okay.
Okay? So that's basically what we're saying, isn't it? We're saying
Yeah.
currently we employ 10, they can output 60. If we hire another one, the rate goes down by 2. Okay? So, is there sort of a nice function we can actually write there? So, by adding X people, we are outputting how many? Well, if we don't add anyone, X equals 0, we've got 60. If we add 1, we reduce that output by 2. If we hire 3, if we hire 2 people, we reduce by 4, and so on. So, basically, this goes down by this factor. So, this basically captures this table quite nicely. So, well, basically what you could do, obviously, if you are completely stuck in terms of working that out, you could say, okay, that's 600. You've got a calculator, haven't you? 11 times 58, that's 638. 12 times 56 is 672, and so on. So you could actually work this out, obviously going and so on, or and basically come up with the answers that way. That's a cheat.
And can you do that in the test?
Well, you can, yes. Obviously, that wouldn't really be the way I would want to solve it, but yes, you would get points for it because you have to get the right answer. But hopefully, my question is not solved that way. A couple of people did that in the exam, I think. So they just miscalculated that one as well. Anyway, so this is the output. So y equals, if you then do it, work it out, 600 plus 60x minus 20x squared, is that right? Sorry, what am I doing? 600 plus 60x minus 20x minus 2x squared. So that's equal to 600 plus 40x minus 2x squared.
Yes, I'm on.
Okay. So we now want to find out when this basically has a local maximum. So we want to maximize the number of outputs, so we need to find out when that's this function here, which some sort of parabola, and looks like this. We want to find out where it's got its maximum. So all we need to do is take the derivative of this. So taking the derivative of this, so y dash equals, well, 600 goes, 40 stays, minus 4x. Okay, so that's basically the derivative. And you want to find out basically when this is 0. So setting this to 0, so 40 minus 4x equals 0. Well, that gives us an answer of x equals 10. And basically, that's our answer. So if you plug in 10 here, so 20, basically 20, that gives you 40 here, gives you 800. If I add one more, 21, I'm down to 38. And I'll do 90 here as well, just to make sure. So that's 42. So if you've got 21 times 38, that's 798. So that's lower. If you've got 19 times 42, that's 840, that's also 792. So, as you can see, up to 19, well, up to 20 you're increasing the output, just about. I'm not quite sure whether that extra person is worth the extra 2 widgets, but that's a business decision. But as soon as you get another one, basically the output goes down again. So the proper answer is probably saying, well, you only hire 19 because those extra 2 widgets are probably not worth the amount of money you have to pay that extra person you hire it. But in terms of the exam question, it would have been 10. So 20 is the maximum number of people you need to get the maximum output. Okay, does that make sense? Good. Have you been able to narrow down your question about maths a bit more?
Not optimization.
Okay.
Limits,
You're still saying everything else. I think a bit more specific.
not differentiation.
Everything.
Everything except for differentiation. Okay. Well, do you know how to draw a graph of function to determine its range? Okay. So that's, I don't need to cover that, or do you want to cover that too?
Do that.
Just gonna.
Do that. If you come back with something more specific, I can help you.
Okay.
Anything else that you guys want to know? Yeah.
Can you go through that Alice, Bob, and Charlie, like where they lie about each other?
Oh.
Do you still have that version?
Yes, I do. You mean the original ones? Alice and Bob?
Yeah, it was on one of the past bits.
Okay.
It's the only past bit that has a solution.
It didn't have a solution, or did it have a solution?
It did.
It didn't?
It's the only past bit that has a solution.
Okay, so it was last year, sir. Okay. Differentiation. Must be here then. Oh yeah, okay, that's this one. This was here. Three people, and this one from Carol. One of them is a liar. One a truth teller and one a normal person. Truth teller always tells the truth, liar always lies, and a normal person, well, lies or tells the truth. So, this time it's got three states. So you can be either a truth teller,
Yeah, you can't. I might get on it.
a liar, or normal person. Okay, so basically you've got additional information. We know that one of them is a liar, one of them is a truth teller, one of them is a normal person. Okay? So we can work through all the different states this way. So A is either truth teller, then Bob must be the liar, and Carol must be the normal person, or Bob is a normal person, and Carol is a liar. Next is A is a normal person, then Bob can be the truth teller, but then Carol needs to be the liar. Normal person, or the other way around. And last but not least, Alice is the liar, Bob is the truth teller, or Carol is the normal person, or the other way around again. These are the only possibilities you've got. Okay? So, now we've got these three statements, S1, S2, and S3. So, basically, let's have a look. So statement 1 is Carol's a liar. Alice says Carol's a liar. Alice is the truth teller. And basically, she's saying that Carol is a liar, which is basically false, because in this scenario, Carol is a normal person, and Alice, as the truth teller, wouldn't say that. So that's a false statement. So basically, I could stop there already, because that has no chance of actually being true. But we can just go through it as well. So Bob says Alice is the truth teller. Now Bob is a liar, so he wouldn't say that Alice is the truth teller, because that would be telling the truth, which you can't do. So that's false again. Carol, being a normal person, can say pretty much anything, saying I'm normal. Basically, since she's either a liar or a truth teller, that basically means that statement is true. So, fair enough, but we don't really care anyway. Next one, basically, we've got Alice still being the truth teller, Bob being normal, and Carol being the liar. So what can we say? Carol's a liar? Yep, that's true. Bob says Alice is the truth teller. Well, that's possible for them to say. Yep. And last but not least, Carol says I am normal, which is a true statement because they're lies. So they can say it. So in this case, we've got them all three being true. Okay? And you go through that for the rest of the table. I won't go through that in painful detail because you can sort of work it out hopefully now. But effectively what you'll then find is this is the only possible line where all of them can actually state what they're stating, which means that's the setup. So as the truth teller, Bob is normal, and Carol is liar. Does that make sense? Good. Any other questions?
Optimization.
Other optimization questions, please. Anyone in particular?
Sorry, I've got
Example 12, 13. Okay.
Oh, really?
Which is
I wish. That's the next one.
this one. Is that this one? Hello? Is that this one? Yeah?
I know.
Okay. Right. Okay, so what we know is that every kilometre on land costs X amount, so £1,000 I think, and the work takes 5 days. And underwater, each kilometre costs £2,000 and takes 15 working days. Okay, so effectively what we want is what route should we follow to actually minimize those costs. So if we put an X here,